Okay, so this we'll talk about standing waves and strings. To understand how they form, we need to understand the principle of superposition, which is when two waves will superimpose upon each other, creating a resultant displacement, either bigger or smaller than their individual displacements or amplitudes. So for example, these two wave pulses, which are travelling towards each other, a short time later could end up looking something like this as they meet, and after they pass through each other, of course, they will continue on in opposite directions away from each other. It's the central picture, this one here. At that moment we call that a superimposed wave, where the displacements have constructively added together. So stationary waves, also called standing waves, they are essentially a store of energy rather than a transmission of energy, like in a progressive wave. So a definition: a stationary wave is the result of two progressive waves, which means two moving waves of the same frequency travelling in opposite directions along the same line. So these two waves will add together, like I just showed you, and form a bigger or smaller wave depending on their phase difference. If the phase difference between the two waves is correct when they meet, a nice clear stationary wave is formed, like in this diagram here. There are two key words to understand: antinodes and nodes. And so a node is a point having zero displacement at all times, formed when two waves meet in antiphase, which means 180 degrees out of phase or out of sync. And this results in destructive interference, where cancellation of the wave energy occurs. An antinode is a point for which amplitude is maximum, and this is formed when two waves meet in phase, resulting in constructive interference. There's no diagram right here, but we'll see one soon. Between any two nodes, all the particles vibrate in phase, but have different amplitudes. Adjacent nodes, or nodes next to each other, are half a wavelength apart. Now we're looking at these standing waves or stationary waves when they form on a string. If you stretch a string very tightly, and you can then pluck or bow it, and that initial energy of the bow or the pluck will be vibrated down the string, and depending on the length of the string you will get particular standing waves formed. There are a couple of equations which relate to the speed of the wave in the string. The second one is the most important one for us, but the first equation, involving tension and mass per unit length, is of interest. We can, of course, we are familiar with tension being increased when you are wiring up a guitar and so on. But if the wave speed in a string is fixed, and that means the tension and the mass per unit length are held constant, then the wavelength and frequency produced of these standing waves depends only on the length of the string. And we're going to focus our attention mainly on this relationship. So we get particular harmonics depending on the length that are possible. So if we have a string fixed at the two ends, then we can get the first, or the fundamental frequency, called the first harmonic, which looks like this. It's basically the longest possible wave that could be held in the string. And it will of course appear to oscillate back and forward between these two positions, and that's called the standing wave, the fundamental standing wave. The second harmonic is basically twice the frequency of that first one, so we end up getting a shape like this, where we now have two antinodes, and we have a central node in the middle where the string appears not to be moving, and so these two parts essentially vibrate back and forth like so. And finally, on the slide we have the third harmonic, which means we're going to have two nodes in the middle, and the wave will look something like this. So here we have 2 nodes in the middle and 2 at the end, of course. Now we have 3 antinodes, and the string will appear to vibrate back and forward at these positions. Notice these formulas on the side here describing the relationship between the wavelength lambda and the length L of the string for each of these harmonics. Now there can be any number of harmonics set up on a string, starting always though with the fundamental where we set n equals 1. N is just the number of the harmonic. You can see it increases, n equals 5 is also possible, and even more, depending on the tension and mass per unit length of the string. So for strings there is a sequence of possible harmonics in terms of wavelengths. We can try and find a pattern. The wavelength for the first harmonic is 2L upon 1. For the second harmonic it's 2L upon 2. For the third harmonic 2L upon 3, and so on. So the pattern for any particular harmonic n in terms of the wavelength will be equal to 2L upon n, where n is the number of the harmonic. So n can be any number, 1, 2, 3, 4, 5, and so on. The question now is, what is the allowable harmonic series of frequencies for a string of given length, mass and tension? Well, we need to realize that we need to use the wave equation, where the wavelength of any particular harmonic n is related to the frequency by this equation, v upon the frequency. Now, rearranging that to make the frequency the subject, we of course divide the wave speed by the wavelength, and then we can substitute in this general formula here instead of the lambda subscript n symbol. So we'll end up with n times v over 2L for any particular frequency of the nth harmonic.